A generation ship is a massive, comparatively slow vessel designed for interstellar voyages. Also known as a star arc, it represents an alternative to spacecraft that travel at significantly higher velocities. But how feasible is this concept? And will humanity ever achieve such journeys in reality? This very question has captivated writers, researchers, and dreamers for ages. Perhaps the earliest and most detailed depiction of a generation ship can be found in Don Wilcox's book, The Voyage That Lasted 600 Years. Robert Heinlein, in his novel Starship, first proposed that the crew of such a vessel might eventually forget their deep space journey, coming to believe they were inhabitants of a confined miniature world. This theme was also explored in an episode of Star Trek. We can also recall authors like Brian Aldiss with Non-Stop, Harry Harrison with Captive Universe, and Boris Lapin with The First Step, among others. Regardless, such a vessel would function as a microcosm of human civilization, supporting a substantial and highly diverse population. It would house numerous educational and medical facilities, food production zones, research laboratories, and more. In essence, it would be a miniature nomadic planet. There's a certain strange allure to this idea, isn't there? Although, undoubtedly, it would be exceedingly difficult in practice to voluntarily confine oneself to such conditions, knowing that death would inevitably arrive at some point before reaching the ultimate destination. But let's not dwell on the somber aspects. Let's embark on such a voyage. Perhaps we can make it work. While warp drives and ion propulsion sound marvelous, they would be of little use if our interstellar travelers perished from starvation or suffocation long before leaving our solar system. Therefore, we must consider the ecosystem that an interstellar human population would need to establish amongst the stars. We need to shift our perspective from an industrial view of reality to an ecological one. Regrettably, even with the most advanced technologies, humanity still struggles to break free from its cradle. Of course, several ideas exist, but some may only become attainable in the distant future, while others remain mere theories and might never materialize. But can such trifles deter us? Not today. So aboard our hypothetical starship, we must traverse a vast distance, let's say 12 light years to a sun-like star, Tau Ceti, at an immense speed, perhaps 10 million kilometers per hour, or 0.01% of light speed. The stakes are high, so let's hope we find life there. For such a journey, we would require an enormous star arc, because several generations must pass on board during the voyage. Furthermore, the number of colonists must be substantial. Otherwise, genetic diseases would be unavoidable. Additionally, for contingencies, catastrophic events have been factored into the calculations, such as a collision with a meteorite. Indeed, even a tiny fragment could cause damage at such velocities, potentially proving fatal to the entire mission. However, let's assume we've devised a robust shield and radiator positioned at the front of the ship to dissipate heat through radiation into space. To continue the mission, we would also have to concede its size, as it's highly probable that enormous fuel tanks would be necessary to lift the shield and radiator along with the ship from Earth. Of course, we cannot overlook onboard epidemics and illnesses, which could potentially reduce the colonist population by 30% at some point. Considering all these factors, according to the most modest and conservative estimates by researchers, the initial number of colonists should be 98 individuals, Moreover, all 49 married couples must be selected based on DNA analysis to ensure maximum genetic diversity. If a more modest crew embarks, the mission's success would be jeopardized. For instance, the survival chances for 25 married couples are estimated at only around 50%. And if there are merely 32 or fewer settlers, the algorithm assigns them no chance of success at all. Their descendants might reach their destination, but by then, they would be incapable of establishing a viable colony. The question arises, what if we employ cryonics or anabiosis? Such hibernation could be beneficial, helping travelers conserve emotional resources and avoid burnout. Yes, this is a possibility, but only for short durations, far shorter than we might imagine, as such dormancy carries risks even when humans undergo it for a few months. Certainly not for years. The consequences could be irreversible, leaving a capable crew as depleted and depression-prone wanderers. It's better to return to the original scenario. So after departing Earth, 98 space travelers will give birth to children, and those children will have grandchildren during the lifetime of the first generation. Thus, according to calculations, the maximum population on the Ark could reach 500 people. This means the colonists will have to provide their own sustenance, meaning they must cultivate it directly on the ship. But how much provision will they need? This, in turn, dictates the ship's size and, consequently, the energy expenditure for its propulsion. For such calculations, we would need to consider not only the crew size, but also the average age of the starship's inhabitants, their height, weight, and physical activity levels to determine their annual caloric needs. Let's not torment the colonists with 3D printed cookies. Instead, let's calculate consumption based on a normal diet. This means the ship must accommodate not only the cultivation of fruits and vegetables, including the production of sugar and vegetable oil, but also animal husbandry, meaning the production of meat, fish, and dairy products. Surprisingly, considering the use of modern technologies like aeroponics, growing plants in an aerial environment without soil, it takes only 10 years to reach a new world, a new planet, a new hope for humanity. Or perhaps, by the time the colonists arrive, the planet has become uninhabitable, or maybe it's already occupied. Nobody can know for sure. As we can see, some sacrifices had to be made, and some aspects simply imagined for our journey. Yes, interstellar travel remains science fiction for us, but what fiction doesn't eventually become reality? The challenges of interstellar flight exist, but that doesn't mean they are insurmountable. Humanity is born to overcome difficulties and evolve. Science not only progresses but accelerates. Since we are reaching for space and discussing options for interstellar travel, it means we will undoubtedly achieve it someday. The concept of space settlements was popularized by science fiction writer Larry Niven. His Ringworld series of 4 novels achieved global acclaim, with the first book published in 1970. The work received numerous awards and accolades, although specialists emphasized that such a ring would be unstable. However, the idea of an orbital city was first proposed by the great Russian scientist Konstantin Tsiolkovsky. He suggested creating cities that would rotate around their axes, resembling rings or cosmic donuts in shape. In 1952, German-born and later American scientist Werner von Braun published his article convincingly arguing for the necessity of such settlements. In this same publication, readers could first see the infamous Donut City, nicknamed the Toroidal Settlement or Torus. In the 1960s, specialists from the American Astronautical Society adopted and developed these ideas. By the mid 70s, a meticulously detailed project for space settlements emerged. In fact, not one, but three such projects existed, all developed by specialists from Stanford University. One of these projects was aptly named the Stanford Torus. It was a truly colossal space station, shaped like a ring. The settlement's diameter was almost 2 kilometers, capable of housing between 10,000 and 140,000 people. The central part of the structure remained stationary, while the ring's rotation around it would take 1 minute. From the inside, the creators envisioned the donut-shaped ring as a vast natural valley where plants could be grown and animals, including chickens, could be raised. The station's axis featured mirrors designed to reflect sunlight onto the inner surface of the torus. This was how the city would receive solar illumination. At the center of the structure was a hub connected to the ring by 6 corridors. Movement within these corridors could be done on foot or by transport. Due to lower gravity, the central section was best suited as a docking bay. Ships from Earth would arrive at and depart from the Stanford Torus. An orbital city could weigh nearly 10 million tons. Clearly, constructing such a behemoth in a short period would be impossible, and the creation of the torus could span a decade. Materials for the station presented another significant challenge. According to the plans, most of them were to be sourced from the moon, utilizing an electromagnetic catapult. However, the realization of such ideas was out of the question. Therefore, in the mid-70s, Stanford University researchers proposed a simplified version, the O'Neill cylinder, also known as Bernal sphere. The sphere's diameter was more modest, not 2 kilometers, but only 500 meters. Consequently, the population of such a station could accommodate a maximum of 1,000 people. This object was named Island 1. Sometime later, a slightly more ambitious project, Island 2, appeared. Now, the Bernal sphere resembled its distant predecessor, transforming from a large space station into a vast orbital settlement. Disregarding their size, all other Bernal sphere models were similar. They were giant space stations suitable for permanent habitation. Living quarters were located within the rotating structure, thereby creating artificial gravity. And thanks to the spherical shape, the inventors aimed to avoid radiation problems, as the outer surface area of the Bernal sphere was optimal for radiation shielding, while the internal volume was sufficient for a closed ecosystem. Interestingly, the object's size and the number of its inhabitants were not arbitrarily chosen. According to the inventors, only such a sphere volume would allow for the creation of a self-sufficient city. For normal life, the Bernal sphere would need its own industry and agriculture. As with the Stanford Torus, sunlight would reach the station via a special mirror system. The third notable project for a space settlement is the O'Neill cylinders, also known as Island 3. It consists of 2 cylinders, rotating in opposite directions. The diameter of each is 8 kilometers, and the length is just under 32 kilometers. Each cylinder has an outer ring with a diameter reaching 16 kilometers. The rotation of the cylinders would generate artificial gravity, requiring them to complete approximately 40 revolutions per hour. The atmospheric pressure inside the station was intended to be half that of Earth's. The most incredible cosmic structure could be considered the Dyson sphere, named after its creator, American theoretical physicist Freeman Dyson. This astroengineering feat represents a spherical shell with a star at its center. Such an object could maximize the utilization of the star's energy, but its realization remains a task for the very distant future. One of the fundamental problems with a Dyson sphere is the inability to balance the gravitational forces of the central star, posing a high risk of self-destruction. All these projects, Stanford torus, Bernal sphere, and O'Neill cylinders, took off in the mid-1970s and were further developed by enthusiasts in subsequent decades. Other designers built upon their ideas. And although these concepts have attracted attention numerous times, no one has dared to set precise implementation deadlines. Regarding the financial aspect, the cost of such a project could reach around $200 billion, even by mid-1970s standards. In our current era, when the romance of spaceflight seems to have faded, the idea of space settlements continues to evolve. Of course, the scale of the ideas is much more modest, and the topic has become the domain of hobbyists rather than professionals. It would seem the benefits of creating orbital settlements are obvious, but this task involves very real risks. Space settlements are truly enormous, and it remains unclear how to avoid meteorite collisions. Even meeting a single one could lead to catastrophe. Another pressing issue is sabotage. The threat of terrorism is more relevant now than ever, and it appears this threat will not disappear in the future. Problems of radiation, fuel, and food also remain significant. None of these issues have been fully resolved, and the idea of sourcing raw materials from the moon seems overly fantastical. Perhaps a space elevator could offer a solution, but its prospects are currently very dim. Paradoxically, orbital cities are now something of the past rather than the future. Mid-20th century engineers could easily imagine people living aboard a giant aircraft by the end of the century. Now, it is very difficult to envision anything similar, even in the distant future. Humanity has concluded that conserving resources is far more important than realizing another monumental construction project. It is crucial to remember this more often. Nevertheless, it is entirely possible that the creation of the first, and certainly very modest, space settlement will appear by the year 2010, provided, of course, that humanity continues to advance technologically. The construction of such colonies would significantly accelerate space exploration, as spacecraft could launch from orbital platforms, making their operation cost-effective due to weightlessness. It is known that overcoming the initial 150 kilometers by rocket during an Earth launch is the most expensive phase of flight, meaning such a station would be extremely useful in Earth's orbit. What are your thoughts on all this? Please share your ideas. It will be interesting to read them. Humanity's aspiration to colonize Mars is often considered to exceed its capabilities. However, not everyone would agree with this assessment. Regardless, progress marches forward, which inspires a certain optimism. For instance, scientists propose using inflatable complexes for housing, digging tunnels into the rock, or constructing homes from local soil. There is also increasing consideration of using artificial greenery on Mars, capable of producing pure oxygen for breathing by utilizing only water obtainable from glaciers and sunlight from solar panels as a growth source. As for food, we have already learned to grow some vegetables in microgravity conditions. However, the risk of failure in hydroponic farms cannot be entirely ruled out. Hence the resort to the admittedly questionable solution of 3D printed food. This is not merely a cake with the taste of ash, but almost real food with flavor additives and all necessary vitamins. Undoubtedly, these are excellent achievements, but it seems they are insufficient to establish a colony on the red planet. Still, let's try to imagine. So, if everything goes according to plan, one day, not too far in the future, a group of astronauts will embark on a long journey to Mars. Our team has successfully launched and is en route to the red planet. During the 7 to 8 month transit, the members of the small crew will be confined to a compact spacecraft with little opportunity for rest or privacy and not much to occupy them. Movies and Tetris will have to suffice. Gradually moving away from Earth, the astronauts will increasingly feel their isolation from everything they have ever known. Real-time communication with command or family will be impossible. There is also a list of potential ailments and incidents comprising 100 diseases and occurrences that could happen during the space journey. Among these are pancreatitis, lumbar spine injury, cosmic radiation, visual and behavioral disorders, and issues with interaction among crew members and with onboard technologies. But our future colonists have a positive outlook and clearly remember that Valery Polyakov undertook the longest spaceflight. He spent 1 year and 2 months aboard an orbital station and remains healthy. Well, here is the long-awaited moment, landing on Mars. Where will the first Martian colony be located? In a crater, a large canyon on Mars, or Valles Marineris, near the equator, or perhaps somewhere else. It's not the main point. The crucial aspect is that the landing was successful. The colony is deployed. Everyone is in their place and ready for prospective work. But the question remains, how long will this colony endure? To answer this, merely believing in a happy existence is insufficient. But we won't dwell on the gloom either. Instead, let's refer to the experiences and statistics from similar simulations here on Earth. After all, the primary objective of such projects is to determine if humans can live and work in a confined environment. In the distant future, such systems could prove useful, both as autonomous settlements in space and in cases of extreme deterioration of living conditions on Earth. Let's consider the HASS experiment, which concluded not long ago. 4 men and 2 women resided in a specially equipped station beneath the summit of Mauna Loa volcano in Hawaii. The module simulated life on a Martian station. During the experiment, the team demonstrated good results and survival capabilities. For example, the participants conducted an experiment to extract water, which exists on Mars, but is in a deep freeze state. Participants wore sensors that recorded their mood, voice levels, and proximity to others. Compatibility tests and stress levels were conducted. This data will help ensure ideal psychological compatibility for crew members on future Martian missions. After all, in addition to their primary work, they will need to maintain life, including growing food, cleaning, filing reports, all while living in a confined space, in close proximity, and in constant contact with a limited number of people. And if there's a tedious person, a know-it-all, or just an unpleasant individual among them, it could easily affect their psyche and cause stress, jeopardizing the entire colony. This is clearly illustrated in the next project we will examine called Biosphere 2. This structure simulated a closed ecological system. Inside the laboratory were grass, trees, and shrubs, allowing for the cultivation of 46 types of plant based food, as well as fish, shrimp, goats, chickens, and even piglets. 8 people, 4 men, and 4 women became part of the artificial biosphere. They were to spend exactly 2 years in complete isolation from the outside world. The complex was intended to function autonomously, as it contained all the necessary conditions for a normal material cycle. However, something went wrong. People began to experience food shortages, and water accumulated on the glass roof, leading to rain. It could not be eliminated, so the desert gradually turned into a steppe. Insect and microorganism populations rapidly and uncontrollably proliferated, not among humans, but among plants. The oxygen content in the air also worsened, dropping to only 14% compared to the normal 21%. As a result, the well-being of the biosphere to inhabitants deteriorated. Their work capacity significantly decreased. Consequently, one woman severed her finger while operating equipment and left the project. She was fortunate, as the remaining participants continued to suffer. They began to lose weight. They found it difficult to breathe, even when resting. Due to isolation, they started experiencing stress. And any minor issue, like who would be tasked with crushing insects or boiling a chicken, became a source of conflict. The team quickly fractured into 2 opposing factions. One group clamored for an immediate halt to the experiment, while the other insisted on seeing it through to completion. Since the project leadership, amused by the unfolding spectacle, also favored perseverance, both factions were compelled to coexist under the same roof until the project's conclusion. It was a small mercy that they didn't resort to bludgeoning each other with bamboo or corn cobs. Upon its conclusion, the team resembled survivors of a concentration camp. The isolation and arduous conditions inflicted profound, lasting stress. It's conceivable they still awaken in terror, though compassionate medical professionals are always available to assist. One might assume the circumstances were ideal, that every detail was accounted for, and the team successfully passed a test of resilience. Yet, it bears noting that the conditions were far from Martian. After all, on Mars, the foremost task for colonists would be to establish a self-sustaining biological system where nothing is wasted and all byproducts are reintegrated. Simply contemplating this prospect could induce nausea in some. A precarious demise would occur within weeks. Furthermore, no one truly knows how our bodies will react to a gravitational pull of 38% compared to Earth's. On the Moon, with its 18% gravity, things seemed fine, but there wasn't enough time to fully assess the physiological consequences. But this is just the beginning. Given recent data about the Martian surface, we understand it is far from hospitable. In just 1 year of life on the red planet, a colonist would accumulate approximately 15 roentgens of ionizing radiation, which is 300 times the permissible annual dose for nuclear industry workers. This significantly restricts the duration any potential traveler could safely spend on the surface of the red planet, as they could scarcely remain there for more than 500 days without risking their health. Yes, of course, there would be some form of protection, but humans wouldn't be confined perpetually. Even if infrequently, there would be scientific and necessary excursions to the surface for at least a few hours. In such scenarios, an individual could experience acute radiation sickness symptoms akin to those suffered by individuals caught in the blast zone during the Hiroshima disaster. The symptoms would vary, including severe nausea. And if the unfortunate soul were to vomit inside their spacesuit, their stomach's contents would be the last thing they ever saw. This is because the fluid and food particles would clog the air intake channels. But let us not dwell on the grim. Let's imagine a cosmonaut survives the initial radiation onslaught and manages to return to the colony. Yet again, their red blood cells would perish, rendering them highly susceptible to infections and leading to an agonizing demise. My apologies. But do not fret, for we have other colonists. They are safely ensconced within the colony, continuing their research and drilling into the Martian crust. However, individuals in isolation, even among others, are prone to depression. Minor setbacks, such as torn trousers or pilfered three-dimensional cookies, could provoke intense anger. Then there are personal grievances, intrigue, and conspiracies. All of these would be amplified manifold, potentially leading to extreme anxiety and outright rage. Over time, the ability to form social bonds, work, entertain oneself, maintain employment, and derive pleasure from Martian life could deteriorate. The situation is even more dire for those predisposed to mental illness, which could manifest far from Earth, and panic attacks could escalate into something truly perilous for the entire colony. If you believe events would unfold differently, your own spacefaring narrative would be most interesting to hear. One day, humanity will learn to inhabit Titan, the largest moon of Saturn. They will harness energy from its boundless fossil fuel reserves and extract oxygen from frozen water, which constitutes a significant portion of Titan's mass. Its nitrogen-rich atmosphere, denser than Earth's, will shield inhabitants from cosmic radiation, allowing them to live in unpressurized structures and travel not in spacesuits, but in exceptionally warm clothing and respirators. People will navigate boats across lakes of liquid methane and soar like birds in the cold, dense atmosphere using wings strapped to their backs. The indigenous mode of transport will be specialized thermal aerostats designed for Titan's atmosphere. For context, one of the earliest proposed projects was named Mangelfair, developed back in the 1970s. It possesses an atmosphere, water, and energy resources. Power plants will run on hydrocarbon fuels. Wind turbines and solar panels will provide supplementary energy. Food is envisioned to be cultivated in greenhouses, simultaneously reprocessing the carbon dioxide released from combustion back into oxygen. From local raw materials, plastic goods can be manufactured, and asteroids can be mined for metals and other heavy elements. Some may dismiss this as naive fantasy, but do not jump to conclusions. It is true that humanity is not yet ready for long-distance spaceflight, at least not in our lifetime, and most likely not in this century. However, as time progresses, this could very well become a reality. The crucial question is, how accommodating will Titan prove to be? I propose we examine the potential for colonization and survival on Saturn's moon without preconceived notions. As it stands, Titan's frigid, somber skies are uninviting and incredibly distant. Titan's surface primarily consists of water ice and sedimentary organic compounds. The moon is geologically young and largely flat, save for a scattering of mountainous formations and craters, along with a few cryovolcanoes. Nevertheless, Titan and Antarctica share certain similarities. Survival in these locales necessitates the active deployment of technology, with heating being paramount. Both destinations require the transport of supplies. To reside permanently in such a place without external support, a source of energy and indoor food production would be indispensable. On Titan, fuel lies readily on the surface, but oxygen must be extracted from subterranean reserves. In both cases, appropriate attire is essential for venturing outdoors. Weasel fur coats will not suffice. Entirely different technologies are required. Titan's temperature plummets far below any terrestrial location, fluctuating around minus 180 degrees Celsius. It is so cold that one wouldn't even have time to fall ill. But that is not all. Unnavigable weather conditions are also characterized by rain, composed of methane and ethane, which then flows into hydrocarbon seas. Nevertheless, the weather there is calmer than in Antarctica. As we know, Earth's atmosphere comprises nearly 80% nitrogen and 20% oxygen. Titan's atmosphere, however, is 95% nitrogen and only 5% methane. We cannot survive without oxygen. Yet, Titan's air is not an immediate poison. It contains enough cyanide to induce severe headaches. Nitrogen, familiar to divers, can cause narcosis, a reversible state akin to intoxication. But do not be deceived. It offers little pleasantness. In practice, if a breathing apparatus were to fail, one would lose consciousness within a minute, but could be revived with timely access to oxygen. Alternatively, carrying plants and consuming them in emergencies to replenish depleted oxygen might be considered. It's unlikely to salvage the situation, but it might offer some reassurance. Titan's atmospheric pressure is 50% higher than Earth's. This atmosphere is more than adequate for protection against radiation and micrometeorites. Due to the cold, the air is also 4 times denser than on Earth. This results in two curious side effects. The first is slowly changing, stable weather patterns. The second is the weak gravitational pull on Titan, which is only 14% of Earth's. With such a ratio, one could easily ascend into the sky using simple devices, such as a so-called wing and a modest propulsion system. Such a flight would prove quite exhilarating and relatively safe, an excellent method for exploring Titan's territories. Colonists will also be dependent on artificial illumination. Anyone who has lived in northern latitudes understands how natural light and darkness dictate life, influencing mood and productivity both indoors and outdoors. At the poles, the sun shines all summer, and perpetual night reigns all winter. Due to the disruption of circadian rhythms, insufficient bright light, and vitamin D deficiency, many people succumb to depression and seasonal affective disorder. On Titan, the situation is considerably worse. Indoor lighting and a suitable diet will be a year-round necessity. Natural cycles of light and darkness will be entirely unfamiliar. As a moon of Saturn, Titan always presents the same face to it. A colony would undoubtedly be established on the side of Titan facing Saturn. In this location, light reflected from Saturn would likely maintain a dim illumination throughout the day, except during periods when Titan enters Saturn's shadow. Consequently, a day lasts 16 Terran days. Thus, for a couple of weeks, illumination will be slightly amplified by the sun, followed by a darker couple of weeks. A year on Titan equates to 29 Terran years, meaning each of the 4 seasons lasts approximately 7.5 years. That is a considerable duration, is it not? Nevertheless, Titan might prove to be the sole location in our solar system where establishing a self-sufficient permanent colony makes sense. While the Moon and Mars appear as relatively sensible options, they present significant drawbacks. Both celestial bodies possess virtually no magnetosphere or atmosphere. The surfaces of the Moon and Mars are constantly bombarded by galactic cosmic rays, energetic particles from distant supernova, and humans cannot endure their onslaught for long periods and remain cheerful colonists. Moreover, the carcinogenic nature of this potent radiation has long been known, though it remains difficult to quantify. Galactic cosmic rays include particles such as iron nuclei traveling at speeds approaching the speed of light, which can damage brain tissue. And chamomile tea will not help here. On Earth, water in our atmosphere shields us from galactic cosmic rays. To block rays from outer space, a layer of water at least 2 meters thick is required. In practice, to protect against radiation, a colony on the Moon or Mars would need to be constructed underground, which is a considerable undertaking. However, for radiation protection, Titan possesses an atmosphere composed of nitrogen, 50% denser than Earth's atmosphere. Saturn's magnetosphere offers additional shielding, and Titan's surface is abundant with hydrocarbons in both liquid and solid forms. These can be utilized as energy sources. Despite the absence of oxygen in the atmosphere, breathable oxygen and fuel for hydrocarbon combustion can be obtained from the water ice beneath the surface. This would require substantial resources and energy. Energy can be sourced in several ways. Method 1: wind turbines. However, there are significant concerns that on Titan, this method will not serve as a long-term energy source, as sand dunes visually demonstrate the low wind activity in the lower atmosphere. Huygens confirmed this in 2005. Second method: solar energy. But therein lies another problem. Titan is nearly 10 times farther from the Sun than Earth, and receives only 1/10 of the sunlight our planet does. Additionally, atmospheric haze filters out some light, making the brightest, sunniest day on Titan resemble twilight on Earth. It is highly probable that this will be insufficient for a colony. The most promising option today might be the installation of tidal turbines, as Saturn generates strong tides on Titan. The Moon's largest hydrocarbon sea, Kraken Mare, rises and falls a full meter daily. Tidal waves surge through the Kraken's throat, a narrow strait separating the northern and southern portions of the sea. This is akin to the Strait of Gibraltar, where a hydroelectric power station could feasibly be installed. And what conclusion can we draw? Titan indeed possesses all the necessary energy resources to sustain human civilization, but living there would be lethally dangerous. Simply reaching Titan would require 3 to 6 years. Yes, that sounds like a long time because it is. During that period, one could go mad aboard a spacecraft. And even if you land successfully, you will not find a delightful planet teeming with rich flora and fauna, but a desert of organic matter, where the atmospheric pressure is 1.5 times that of Earth's, and a gravity approximately 7 times lower than Earth's could cause muscle ailments. An atmosphere of nitrogen, methane, and hydrogen allows breathing only artificial oxygen, which would also adversely affect health. And the low temperatures would present an additional obstacle to comfortable existence and mobility. Emotionally and mentally, you would undoubtedly face challenges. It's quite possible you'll want to weep, but you'll have to learn to cry without tears, as water is an unaffordable luxury. Now, the paramount question: If you had the opportunity to travel to Titan and become part of a colony, would you seize that chance? Skulls, faces, and much more. Naturally, we are all affected similarly. What? You haven't reconsidered traveling to another planet, though it no longer matters. The space shuttle is already waiting to depart for the smallest and closest planet in our solar system, Mercury. We are fortunate. It is a terrestrial planet, meaning one can walk on it with relative ease. In many respects, it resembles the lunar surface as it is heavily cratered. However, you are unlikely to engage in agriculture here. Pumpkins will not grow here. Analysis of the planet's elemental composition shows it is similar to certain regions on Earth and poor in aluminum, calcium, titanium, and iron. However, it is rich in magnesium and sulfur. The planet possesses a magnetic field strong enough to influence solar wind, thus creating a magnetosphere. However, it is still insufficient for human life, being approximately 100 times weaker than Earth's. Furthermore, there are areas within the magnetosphere with reduced magnetic field intensity, allowing charged particles from the solar wind to reach Mercury's surface. This, in turn, results in severe radiation for humans. But as an option, burying oneself a bit deeper might allow for habitation. It would be dark and frightening, but safe. Additionally, if you've ever complained about not having enough hours in the day to accomplish your tasks, Mercury would be an excellent choice, as one day here lasts a staggering 59 Earth days. You could accomplish, well, just a whole lot, and you could celebrate New Year's every 88 days, for that is precisely how long it takes the planet to orbit the Sun. Mercury has virtually no atmosphere, so the sky there is always black, which is undoubtedly a significant advantage for stargazing enthusiasts. So don't forget to bring your telescope. The Sun appears 2.5 times larger than it does from Earth. Mercury's day side heats up to 420 degrees Celsius, while the night side cools down to minus 180 degrees Celsius. But if you find yourself on the border between them, at the so-called terminator, no, not that terminator, but the terminator dividing light from darkness, the boundary separating the illuminated part of the body from the unilluminated dark part, you might be able to survive as long as you can do without oxygen, as the planet's surface is nearly a vacuum. Therefore, without specialized equipment providing oxygen, you won't manage. Or, after millennia, you would have to evolve into some primitive life form, like human tardigrades, which, as it turns out, fare quite well in a vacuum by entering a state of suspended animation. However, sleeping through one's entire life is not exactly an appealing prospect, so let's move on. Venus is also a planet with a solid surface. However, standing on it would be very difficult. Venus has nearly the same gravitational force as Earth, but its atmosphere, composed of carbon dioxide, is much denser. The air is so thick that moving within it is challenging, akin to being in the Pacific Ocean at a depth of 914 meters. A day on Venus lasts 116 Earth days. However, the atmosphere poorly transmits sunlight, and the surface is very dark. The greenhouse effect heats the planet to 465 degrees Celsius, causing constant rains of sulfuric acid, which at the surface transform into mists, also of sulfuric acid. So if you found yourself on Venus, you would be immediately crushed by the atmosphere and burned by the heat and sulfuric acid. My apologies. Similar conditions exist here on Earth. Consider, for instance, hydrothermal vents at the bottom of the oceans. The water temperature there can reach 400 degrees Celsius, and it contains a high concentration of hydrogen sulfide, sulfides, and other impurities detrimental to humans. Nevertheless, bacteria adapted to these conditions thrive there. Therefore, in Venus's case, human evolution would need to take a step backward. Alternatively, one would need to become titanium, nickel, or preferably platinum mutants. Therefore, it would consume less food than on Earth. The digestive system would shrink, and the colonists' bodies would become slender, perhaps resembling a cosmic flounder. But that is not certain. When a Martian arrives on Earth, people will see a thin person with brittle bones. A Martian's weight would increase nearly threefold. A 38-kilogram individual on our planet would weigh 100 kilograms. This would place additional strain on their bones. Most likely, they would be unable to move without assistance. They would require a cane or a wheelchair from Elon Musk. If you were to pat the unfortunate Martian on the back as a friendly gesture, you could injure their rib cage. Therefore, never pat Martian inhabitants on the back. On the red planet, under conditions of low gravity, the heart muscle does not need to work as intensely or contract as rapidly to pump blood through the circulatory system as it does on Earth. Consequently, a Martian's heart would become weaker. Under Earth's conditions, it simply could not cope with the load. Mars is much farther from the Sun than Earth. The red planet receives 1.5 times less light. Because of this, colonists' eyes might change. Either the brain will develop a new mechanism, allowing the retina to perceive and process more light from what is available, or over time, the colonists' eyes will become larger, meaning wider. One more important thing. While solar light is scarce on the red planet, the thin Martian atmosphere transmits ultraviolet radiation many times more than Earth's. On our planet, to protect against ultraviolet radiation, skin produces the pigment melanin, or more precisely, its variant, EU, which acts as a natural sunscreen and gives skin a brown hue. Individuals with more E will be better equipped to withstand the extreme ultraviolet radiation on the red planet. Therefore, Martian skin would be much darker than anyone's on Earth. Well, there is a slight glimmer of hope here. However, in reality, there is currently no hope for human evolution on other planets. We will ultimately have to rely on the development of technologies that will enable future Mars colonists to exist in an artificially created environment and protect them from the destructive atmosphere of the cruel red planet. And we are picking up speed, flying onward. A series of gas giants awaits us, and our first stop is Jupiter. If you were to fall onto it from a great height, you would most likely be killed by extremely intense radiation long before approaching the planet's atmosphere. If you survived that and reached the upper atmospheric layers, you would plummet through them at a speed of 180,000 kilometers per hour. Approximately at an altitude of 250 kilometers, you would reach ammonia clouds and experience a temperature of minus 150 degrees Celsius and strong winds. Hurricanes in Jupiter's hydrogen atmosphere reach speeds exceeding 480 kilometers per hour. And yes, the pressure here is already sufficient to be lethal. If all of this means nothing to you, then after 12 hours of continuous descent, you would reach the lower atmospheric layers where impenetrable darkness reigns. The immense pressure here is 2 million times that of Earth's, and the temperature surpasses that found on the Sun's surface. There is simply no time for visual observation of changes. It's either adaptation or immediate disintegration. We continue our journey now approaching Saturn. It presents a different spectacle than Jupiter. Wind speeds on Saturn can reach an astonishing 1,800 kilometers per hour in certain regions, significantly exceeding those on Jupiter. Should you venture into the planet's atmosphere, you would be crushed by the overwhelming pressure and annihilated by the extreme temperatures. The planet's rings might appear alluring, but I must temper your expectations. They are merely a vast collection of tiny ice and dust particles adrift in the void of space. Standing on them would be more precarious than on a skateboard, and establishing any form of habitation there is utterly inconceivable. How about a vacation on Uranus? If you're seeking a getaway destination, this is it. A 2-week terrestrial vacation on this planet would translate to a staggering 3 Earth years. It even boasts a sea, though it's composed of ammonia. Alongside your inflatable mattress, you'd need a thermal imager for visibility in the perpetual darkness and a heavy parka to ward off the intense cold. However, you wouldn't have to worry about pressure, temperature, or radiation. We press onward. Behold Neptune, another gas giant, an ice behemoth. The upper reaches of its atmosphere hover around minus 220 degrees Celsius. Yet, at Neptune's core, temperatures soar to 7,000 degrees Celsius, comparable to the surface of our Sun. The planet's atmosphere is racked by the most ferocious winds in the entire solar system. Estimates suggest their velocities can reach 600 meters per second. And what of the atmospheric composition? The prognosis here is equally grim. Methane, ammonia, and even water, though found only in the deepest atmospheric layers, which would be extraordinarily difficult to reach. The relentless winds would simply sweep you away, preventing any chance of a close encounter, let alone survival. Your only options would be to somehow become significantly denser or to perpetually drift in the upper atmospheric currents for eternity. Perhaps massive wings or a superpower would be necessary to even attempt to alter your position. It appears our grand excursion has reached its conclusion. The voyage was quite extensive, and it's time to return to our familiar home. We hold on to the hope that humanity will continue to discover new worlds suitable for life, establish sprawling metropolises on Mars, and explore the moons of the gas giants. For now, we reside on a truly unique planet, a cradle of life, perfectly suited for its emergence, evolution, and sustenance, including our own existence. This is a world blessed with nature of unparalleled beauty and richness, providing us with all that is currently necessary for our survival. Its name today is Earth. 2 climbers stand triumphantly atop Olympus Mons on Mars, a colossal peak reaching 26,000 meters in height. After a protracted ascent and immense exertion, they have achieved what they've dreamed of since humanity first set foot on the red planet. Is climbing the Martian Olympus even possible? If so, how long would such an expedition entail? What perils await the intrepid travelers? And could this truly be the most arduous climb in human history? To investigate, let us recall Earth's own loftiest mountain. We speak, of course, of Chomolungma, more commonly known as Mount Everest. Its elevation stands at 8,848 meters above sea level. To date, Everest has seen 9,159 successful ascents. Tragically, 308 individuals have perished during Everest expeditions. The primary causes of death include avalanches, falls, and injuries, altitude sickness, frostbite, solar radiation exposure, and other health complications stemming from the extreme conditions of such a climb. Can we anticipate a similar scenario on Olympus Mons? To explore this, let us mentally transport ourselves back to Mars, to the very outset of our hypothetical expedition, and become part of it. Olympus Mons on Mars is the largest volcano known in the entire solar system. Its height from base to summit exceeds 26 kilometers, and it spans 540 kilometers in width. The volcano is even visible from Earth. Before the advent of space probes, the region of Mars where Olympus Mons stands was known as the Snows of Olympus. The volcano reflects sunlight more effectively, appearing as a bright white spot from great distances. It formed during the Diamond Age, a period when Mars ceased to be bombarded by a torrent of meteorites, transforming into the arid, frigid planet we observe today. Crucially, safety. Climbing on Earth necessitates the reciprocal belaying of one climber by another. One person ascends, while the other manages a safety system, ready to intervene and prevent a fall over a shorter distance. This system comprises a rope and a series of anchors secured along the climber's route. Furthermore, we fervently hope that specialized modular backpacks will be equipped with storage for climbing gear and fully operational life support systems. The sheer difficulty of this climb can only be imagined. With all questions of equipment, logistics, and medical preparedness addressed, you embark on your journey. While we draw a comparison between Everest and the Martian Olympus, it's vital to recognize that these are two astonishingly distinct entities. Everest is an entirely different type of mountain. All routes involve varying degrees of challenging rock and ice climbing. Mount Olympus, in contrast, resembles a flattened Martian pancake, vast as France. Indeed, unlike Everest, the slope at Olympus's summit is so gentle that you might not even perceive you are on a mountain. And considering the planet's reduced gravity, it would feel remarkably effortless, as if undertaking merely a 5% incline. It more closely resembles a long walk, a walk that would constitute 70% of the entire ascent. Though you would face a monotonous horizon across a predominantly flat mountain, you would eventually reach the caldera. This is arguably the most breathtaking feature of Olympus Mons. Here, the experience becomes significantly more engaging, as along its entire circumference, you will encounter a series of cliffs ranging from 4 to 6 kilometers in height. It is here that you will truly need your equipment, skills, and climbing prowess, and perhaps a touch of tranquilizer. No, this climb is what you have trained for your entire life. To navigate the labyrinthine cliffs, employing satellite imagery, or more likely, drones, would be a prudent strategy to identify the most straightforward path to your objective. You are embarking on a demanding trek, not only due to the mountainous terrain, but also the altered landscape, which will become increasingly difficult to traverse. Consider, for instance, the volcanic rocks formed from cooling lava that flowed through Martian fissures and conduits. Rocks like kyanite, trachyte, andesite, and basalt. While the terrain is largely blanketed by the red planet's ubiquitous dust, some areas will reveal exposed geological formations. You might find volcanic glass underfoot, tiny crystals known as microlights, and larger fragments within porphyritic extrusions. Navigating such challenging terrain under Martian conditions would be immensely arduous, given that the atmospheric pressure at Olympus Mons's summit is a mere 2% of that found at average Martian surface level. For context, the pressure at the summit of Everest is approximately 25% of sea level pressure. Furthermore, one must account for lethal factors such as temperature fluctuations. During Martian summers, the red planet can warm to 20 degrees Celsius, while nighttime temperatures plummet to minus 90 degrees Celsius. Radiation is another persistent threat. Over the course of a year spent on the red planet, such a traveler would accumulate roughly 15 Roentgens of ionizing radiation, a significant dose comparable to that experienced in nuclear industry environments. However, let us place our faith in the miraculous, or more accurately, in future technologies, or perhaps the fantastical technologies of the distant future, thanks to which, after several weeks, you are not only alive, but have successfully neared your objective. Your group of intrepid travelers, despite radiation exposure, extreme temperature shifts, pressure variations, abrasions, and fractures, has reached the caldera of Olympus Mons, though not all have made it. The volcanic caldera measures 85 kilometers in length and 60 kilometers in width. Its depth reaches 3 kilometers, attributed to the presence of 6 volcanic craters. For comparison, the crater of Mauna Loa, the largest volcano on Earth in Hawaii, measures only 6.5 kilometers in diameter. Now, standing at the highest point, Olympus Mons unfolds a spectacular vista before you. Mars's Olympus Mons is so immense that you can only perceive a fraction of the numerous pits and depressions formed by the caldera. Lava flows, fissures, and several impact craters scar the surface. Dust from annual storms has settled between basaltic formations and flows. At this altitude, your expedition is effectively positioned in the vacuum of space, above the majority of Mars's atmosphere, and stars are readily visible overhead. In the thinner atmosphere below, delicate blue ice crystal clouds begin to appear in the late afternoon sky. Olympus Mons occupies such a vast area that it cannot be fully appreciated from the planet's surface. The distance required to view the volcano in its entirety is so immense that it would be obscured by the planet's curvature. Therefore, a complete profile of Olympus Mons can only be observed from the air or orbit. Similarly, if standing at the volcano's very apex, its slopes would disappear beyond the surface horizon. In any event, you have conquered Olympus. The soiled suits of the expedition members bear testament to the wear and tear accumulated over weeks of arduous climbing up the solar system's most colossal mountain. Starting with 5 participants, only 2 managed to reach the finish line. What transpired with the others? History remains silent. Perhaps it's time to reveal the tale. Nevertheless, a celebration is in order. For this, you've brought along Martian ale. Although, wait, you're wearing a spacesuit. One wonders, how long would it take to ascend Olympus Mons on Mars? Given the aforementioned challenges, it's difficult to say. For comparative purposes, an ascent of Everest typically lasts from 2 to 4 weeks, necessitating frequent stops for acclimatization. If we were to imagine the Martian Olympus on Earth, even more acclimatization stops, additional camps, and more rest for weary travelers would be required. Such an ascent would likely span from 1.5 to 3 months. And that's on Earth. On Mars, it's an entirely different proposition. Fortunately, this particular question is not on the immediate agenda for this generation. Space colonization, planetary terraforming, these are no longer mere concepts confined to science fiction novels, but tangible prospects that occupy our minds in this age of advanced technology. However, the complexity of achieving such feats is contingent upon numerous factors, one of which is the necessity of developing self replicating machines for terraforming celestial bodies and for sustaining the life of colonists. The physicist mathematician John von Neumann, born in 1903, was one of the first to seriously consider this idea. A truly gifted individual, at the tender age of 6, he could mentally divide two 8-digit numbers. Yes, we can do that too, it just requires a calculator. John was always captivated by mathematics, the nature of numbers, and the logic of the world around him. By the age of 8, he had a firm grasp of mathematical analysis. It can be said that von Neumann was impeccable in his scientific pursuits, particularly in areas like extreme physics, chemistry, and the atomic industry. He also played a pivotal role in the development of computers and the ADVC. The scientist introduced the scientific community to the concept of a computer with a stored program, a memory architecture that still bears the name von Neumann architecture and has been implemented in virtually all computers and microprocessors for decades. Later, von Neumann developed the mathematical theory of machines capable of creating exact replicas of themselves. The potential advantages of a self-replicating spacecraft or robot for galactic exploration were discussed by Chris Boyes in his book Extraterrestrial Contact: Personal Perspectives, and by Michael Orbem in Panam Peruma Cameron as early as 1969. The concept posits that a spacecraft capable of generating precise copies of itself could traverse the vastness of space for centuries. But how is this achievable? Let us delve into this idea with von Neumann. Initially, a von Neumann probe, equipped with an interstellar propulsion system and a universal replicator possessing human-level intelligence, is launched from its home star towards a neighboring star system. Upon arrival, it would locate raw materials from local sources, such as asteroids, and utilize them to construct several copies of itself, including its rocket engines. These copies would then be launched towards the next set of adjacent stars. This process would repeat indefinitely, resulting in an ever-increasing number of identical probes venturing into progressively more distant regions of the galaxy. After deploying its duplicates, the probe would commence exploration of the star system it has entered. The objective is to conduct scientific research and transmit the findings back to its point of origin. Such a device could also serve as a means of interstellar colonization. This could be achieved by creating an artificial environment capable of sustaining life, and then implanting synthesized egg cells within it. These cells would contain genomes generated from information stored in the computer's memory. In theory, embryonic life forms within such a colony could be cared for by robots, potentially leading to the emergence of an independently evolving civilization near a new star. The flexibility of the device is a significant advantage of the von Neumann probe. As a universal machine, it can be employed for any purpose within the colonized system, depending entirely on the instructions transmitted by its creators. And as technological progress advances, this device can always be reprogrammed, for instance, to develop faster rocket engines for subsequent generations of probes and space colonies, or to produce more sensitive measurement equipment for exploring a new star system. The time required for the entire galaxy to be fully explored and colonized depends on several factors, including the duration of interstellar travel and the speed at which these devices can reproduce and perform other tasks in their host systems. By the most conservative estimates, approximately 300 million years, or 5% of the galaxy's current age, would be required. However, this is for complete colonization, and by then, we would likely be very old. The approach to colonization using von Neumann probes appears logical and cost effective. Who knows, perhaps this method is already widely employed by advanced civilizations. On the other hand, if highly developed civilizations do exist, it's possible there's an unspoken code of non interference with planets exhibiting a lower level of development compared to their own. This concept gives rise to the zoo hypothesis. It's based on the idea that extraterrestrial civilizations observe the development of life on Earth, much like we observe animals in a zoo, such as aggressive monkeys that pay us no attention. One of the tenets of this theory explains the absence of open contact with extraterrestrial civilizations by Earthlings to date, as a result of our significantly lower level of development compared to theirs. This could imply that while inter-system civilizations might be ready to extend a greeting, our limitations might prevent us from even understanding such an attempt, leading us to react defensively and potentially destroy what we cannot comprehend. From this perspective, we should have discovered them 53 years ago. There probably must be a God, he said to his mother near the end of his life, because it is much harder to explain if there isn't. We press on to the eighth planet in our system. Neptune was not chosen by chance, as it resides at the solar system's periphery and harbors trans-Neptunian objects, which are not only prime potential habitats for life in the cosmos, but also excellent temporary outposts for more distant journeys. Reaching Neptune is no simple feat. It requires traversing 4.5 billion kilometers. With current technology, this equates to approximately 10 years of flight, a decade of arduous travel in confined spaces, relative solitude, and sustenance printed from a 3D printer. Indeed, not everyone could endure such conditions. And even upon reaching the planet, one would realize that modern stations like the ISS are ill-suited for Neptune's orbit, simply because they are technically obsolete, even by today's standards. New technologies, under current circumstances, are unlikely to arrive anytime soon. Furthermore, and sadly, the truth is that once we compared achievements, future plans, and dreams associated with space exploration, we now compare them to Earth. Let us hope that in 100 years, the situation will change, and humanity will finally begin to set appropriate priorities in resource utilization. It is precisely about this time that we will discuss today. So, let us transport ourselves to the year 2012. Incredibly, technologies in the aerospace sector have advanced significantly. Our capabilities for space exploration are far more promising and ambitious. The Moon and Mars already host colonies, providing us with the technology, experience, and a strong desire to push further. Let us imagine that in that distant future, we reach Neptune not in 10 years, but in 10 days. An astonishing vista unfolds before us, a colossal gas giant. The planet's gravitational pull would draw you in with nearly the same force as on Earth. as Neptune's gravity is only 17% stronger than Earth's. This is the closest example of nearly Earth-like gravity in the solar system. Neptune is 17 times more massive than Earth, but also 4 times larger. What we perceive is actually the uppermost layers of very deep gaseous clouds. Should you attempt to stand on one of these cloud tops, you would simply begin to fall through the planet's gaseous layers. During this descent, you would experience a continuous increase in temperature and pressure until you finally reach a solid core. However, the temperature in this region is 1000 degrees Celsius, enough to melt rock. Therefore, it is impossible to stand on Neptune's surface, let alone with feet that would have long since melted. And although Neptune is captivating and possesses some valuable resources, it is not of primary interest to us. However, colonizing its moons presents a more achievable objective. Neptune currently has 14 known moons. The mass of the largest moon accounts for over 99% of the total mass of all of Neptune's moons. Only this moon is massive enough to be spherical. We are referring to Triton. Fortunately, it is within walking distance. We shall set our course for it, as our mission is not merely to reach Neptune, but to establish a colony for further voyages. Unlike all other major moons of planets in the solar system, Triton possesses a retrograde orbit. It was likely captured by Neptune's gravity rather than formed in situ. It may have once been a dwarf planet in the Kuiper Belt. With a diameter of 2,706 kilometers, it is larger than the dwarf planets Pluto and Eris. Triton is one of only 3 planetary moons in the solar system, with an atmosphere alongside Io and Titan. As Neptune completes its 165-year journey around the Sun, Triton's polar regions take turns basking in sunlight. This solar influence causes minor changes on Triton's surface. Frozen nitrogen, methane, and carbon monoxide sublimate into gas, making the atmosphere denser. The atmospheric pressure on Triton is approximately 70,000 times less than on Earth. The object exhibits virtually no noticeable seasonal temperature variations. With an average temperature of minus 235 degrees Celsius, Triton is the coldest body in the solar system. To venture there without meticulously tested equipment would mean remaining forever a frozen part of Triton, which is hardly an appealing prospect for photographs. A day on Triton lasts almost 6 Earth days. During this time, the sun in its sky appears as a small dot, rising in the west and setting in the east. Moreover, Triton is tilted relative to its planet. So if you were on the side of the moon that perpetually faces Neptune, you would see not only Neptune's equatorial region, but also its northern and southern polar regions. Triton distinguishes itself from all other moons in our solar system. If you were to stand on its surface, you would gaze upon Neptune, appearing 10 times larger than Earth's moon. It would undoubtedly be an awe-inspiring spectacle. It remains unclear if Triton possesses any captivating geological formations that future colonists might explore. A circumnavigation of the moon would require over 70 Earth days. This, of course, assumes you could adapt to traversing Triton's remarkably weak gravity, which is approximately half as strong as our moon's. Consequently, the moon is ideal for those who prefer a less active lifestyle. You would practically float, barely touching the ground. Should you decide to contact loved ones during such an excursion, radio signals would reach Earth in 4 hours. It is theorized that Triton harbors a subsurface ocean, a mixture of ammonia and water. The average temperature of this water, if it exists, is unlikely to exceed minus 90 degrees Celsius. However, the ammonia would keep the water in a liquid state. For perspective, there are organisms on Earth capable of surviving at minus 103 degrees Celsius. Accessing the water from this ocean presents a considerable challenge. Nevertheless, the presence of substantial water reserves is the most significant advantage in any colonization scenario. Water from beneath the icy crust could not only fulfill colonists' drinking water needs, but also be utilized for oxygen production. Following this proposed plan, explorers would first establish a small base on the surface. Subsequently, they would commence drilling through the moon's icy shell until reaching the hypothetical subsurface ocean. Colonists would then create, or likely discover, a void between the ice crust and the water's surface. This would shield the colony from Neptune's damaging radiation with a thick ice layer. The existence of liquid water offers hope that temperatures beneath the ice are more accommodating than on the surface. Indeed, colonists could inhabit dwarf planets, utilizing fusion or geothermal heat, and extracting readily available ice for volatile compounds and minerals. Considering the low gravity and, consequently, reduced pressure within the icy mantle or internal ocean, colonizing the outer surface of the rocky core could provide colonists with the most abundant mineral resources, while also protecting them from the cold and conserving energy. Inhabitants of such bodies could also construct rotating habitats or reside underground for decades before venturing further. Due to its unique natural phenomena, Neptune's largest moon has frequently served as a canvas for science fiction writers' imaginations, envisioned as a unique staging post between the solar system and interstellar space. Who knows? Perhaps Triton will one day truly become that. Having forged a path to the stars, humanity almost immediately began dreaming of interstellar and interplanetary voyages. Perhaps we ourselves are among those romantics. However, over the past 100 years, we have come to realize that galactic dispersal might prove an insurmountable task for humankind. After all, to traverse vast interplanetary distances, humanity requires more advanced propulsion systems in the spacecraft, capable of speeds approaching or matching light speed. Otherwise, we will grow old aboard these shuttles, never reaching our destinations. Of course, these vessels, prototypes, and engines exist, though primarily within the writings of authors and futurists, and some even find their conceptual and scientific embodiment. Some are already realized, others remain in prototype status for decades, and a few reside on the fringes of speculation and are highly debated. But perhaps sooner or later, they will prove effective. For a long time, scientists and engineers worldwide have been diligently working on developing alternative spacecraft propulsion systems that could accelerate vessels to record-breaking speeds. Let us examine 7 key concepts in this domain. Project number 1, designated Yaed Edu. This involves a compact gas-cooled fast neutron reactor. Its operational principle relies on the exhaust velocity of its working fluid, which is orders of magnitude greater than the expulsion speed of gases from chemical engines. The fuel would be a uranium carbonate ride, enriched to a degree 20% higher than in conventional reactors with the isotope U-235. The coolant would be a helium-xenon mixture, heated to 1000 degrees Celsius during operation. The advantages of this project include an exceptionally long operational lifespan for the engine, extended intervals between maintenance, and the potential for decade-long service. A single activation for acceleration could be sustained for extended periods, ultimately enabling even faster travel. The engine, powered by a nuclear reactor, would operate continuously throughout the flight. It would accelerate the spacecraft during the first half of the journey and decelerate it during the second. Furthermore, a spacecraft equipped with such an engine would possess maneuverability and acceleration capabilities. Unlike other systems that can only achieve initial velocity, after which they follow a predetermined trajectory. A vessel with this engine could reach Mars and return safely within 30 to 40 days, whereas a journey using current propulsion systems might take considerably longer. Project number 2. This engine is based on a design known as the IM drive. It consists of a cylindrical vessel containing a magnetron that emits electromagnetic waves, similar to those found in a standard microwave oven. This would be sufficient to generate a very small, yet discernible thrust. The creators explain the engine's operation through pressure differentials created by electromagnetic radiation at opposing ends of the device. This generates thrust directed towards the narrower end. The feasibility of this operational principle has been repeatedly challenged, but all experiments with the Schauberger device have demonstrated thrust in the predicted direction. The invention has undergone testing under various conditions, including a vacuum, where it exhibited a thrust of 20 micronewtons. While this is a very small amount compared to chemical rocket engines, according to its developers, the AM drive could operate indefinitely, as the magnetron's function can be powered by solar panels, making it a highly appealing prospect. In theory, a probe equipped with this engine could achieve an acceleration of 600 kilometers per hour over approximately 10 years of flight, covering a distance of about 660 astronomical units. For comparison, the Parker Solar Probe achieved a velocity of only 194 kilometers per hour. To confirm the engine's operational capability, numerous further measurements are required, along with the elimination of any potential side effects, such as those caused by external magnetic fields. The third project worthy of attention is the electric sail. As we know, the sun emits not only photons, but also electrically charged particles, such as electrons, protons, and ions. These collectively form what is known as the solar wind, which continuously ejects approximately 1 million tons of matter from the sun's surface every second. The solar wind, much like atmospheric wind, is suitable for propulsion. All that is needed is to harness it to push sails. Through an electron gun that emits particles in the opposite direction of travel, the spacecraft acquires a positive electrical potential. Since the mass of an electron is approximately 1,800 times less than that of a proton, the electron stream would repel the spacecraft, thereby generating thrust. If successfully implemented, a spacecraft utilizing this technology could reach the heliopause, the boundary of the sun's magnetic field, in just 10 years. This is remarkably fast. For instance, the Voyager probe required 135 years to cover this distance, approximately 120 astronomical units from the sun. Next is the ion engine, a stream of charged particles, or ions, is not only emitted by stars, ionized gas can also be generated artificially. In their normal state, gas particles are electrically neutral, but when their atoms or molecules lose electrons, they become ions. While the gas as a whole remains electrically neutral, its individual particles become charged, meaning they can be influenced by a magnetic field. In an ion engine, an inert gas is ionized by a stream of high energy electrons. These electrons strike the gas atoms, dislodging electrons and giving them a positive charge. These resulting ions are then accelerated in an electrostatic field to speeds on the order of 200 kilometers per second, which is 50 times greater than the exit velocity of gas from chemical rocket engines. Nevertheless, current ion engines produce very low thrust, around 100 million newtons. However, they possess a significant advantage: a high specific impulse, which substantially reduces fuel consumption. The energy for ionizing the gas is derived from solar panels, allowing an ion engine to operate for extended periods, up to 3 years continuously. Over such a duration, it can accelerate a spacecraft to speeds unimaginable for chemical engines. Furthermore, ion engines have already navigated the solar system on various missions, such as the Deep Space One probe, which achieved a velocity increase of 5 kilometers per second. Future improvements aim to significantly enhance this, first to 40 kilometers per second, and then to hundreds and even thousands. Project number 5. This concerns plasma engines, which have been under development since the 1970s. Their operating principle involves achieving plasma state, which requires extremely high temperatures. Therefore, in plasma engines, ionized gas is heated to several million degrees Celsius. This heating is accomplished using an external energy source, such as solar panels, or more realistically, a compact nuclear reactor. The hot plasma is then expelled through the rocket's nozzle, generating thrust hundreds of times greater than that of an ion engine. Unlike ion engines, plasma engines have not yet been tested in space, but they are associated with significant expectations. Theoretically, a spacecraft weighing 100 tons, equipped with a suitably sized plasma engine, could accelerate to 10,000 kilometers per hour second, albeit over 317 years. This is a considerable duration, exceeding human lifespans. We require something more potent, perhaps a fusion engine. Project number 6, a fusion engine. Humanity has been attempting to harness the energy of thermonuclear fusion since the mid-20th century, but success has remained elusive thus far. Nevertheless, controlled thermonuclear fusion remains highly attractive due to its potential as a source of immense energy derived from readily available and inexpensive fuel, isotopes of helium and hydrogen. A fusion reactor within such an engine would consist of a non-magnetic cylindrical chamber ranging from 100 to 300 meters in length and up to 3 meters in diameter. The chamber would be supplied with fuel in the form of high-temperature plasma, which, under sufficient pressure, would undergo a nuclear fusion reaction. Magnetic coils surrounding the chamber would contain this plasma, preventing it from contacting the equipment. The fusion reaction zone would be located along the cylinder's axis. Using magnetic fields, the extremely hot plasma would be expelled through the reactor's nozzle, generating immense thrust, many times greater than that of chemical engines. The plasma temperature during thermonuclear fusion reaches not tens of thousands, but millions of degrees. Consequently, the theoretical specific impulse for a deuterium and helium-3 reaction is 250,000 meters per second, exceeding 7% of the speed of light, which could potentially accelerate an interstellar probe to 30% of light speed. Of course, sufficient fuel must be reserved for deceleration, but even 10 to 15% of light speed is ample for sending probes at least to our nearest stellar neighbors, such as the Alpha Centauri system. This is certainly a significant advancement. One can be confident that fusion-powered shuttlecraft for travel within our solar system will be developed at such velocities. Finally, let us examine the concluding project, one that borders on science fiction. This concerns the VARP drive. This is a hypothetical technology that would enable a ship equipped with such an engine to traverse interstellar distances at speeds exceeding the speed of light. The ship itself would not locally accelerate to near light speeds, yet it would move faster than a flat electromagnetic wave in a vacuum. According to the proposed concept, space-time behind the starship would expand at a tremendous rate, propelling the vessel forward in a straight line. The manipulation of space-time is envisioned through the application of extremely powerful electrostatic fields. Remarkably, a group of researchers is currently investigating methods to bend the trajectory of photons to demonstrate the possibility of faster-than-light travel. This is an exceptionally complex and delicate endeavor, requiring sophisticated equipment. The laboratory itself is not located on Earth. It rests on special pneumatic supports that counteract any ground vibrations that could affect instrument readings. In theory, the capabilities of a warp drive are astonishing, as journeys to neighboring star systems would take mere months or even weeks. For instance, we could reach Alpha Centauri, situated 4.3 light years away, in just 14 days. Naturally, besides energy sources, the particles accelerated during the journey, which could unintentionally be released upon deceleration and annihilate all life, including the crew, are also considered a problem. Furthermore, there is a possibility that deceleration might become impossible once movement begins, meaning the crew could perish, not only from old age, but from a multitude of causes. Nevertheless, mathematical calculations and experimental data suggest that warp drives might have a viable chance. If humanity develops along the correct path, unites, and truly understands its objectives, interstellar travel is possible. Certainly not in the immediate hundreds of years, but possible. This would necessitate not only immense speed, but also a form of spacecraft arc large enough to sustain a community of humans, plants, and animals within a completely closed ecological system. Simultaneously, it must be sufficiently compact to achieve relatively high speeds, thereby reducing the duration of cosmic radiation exposure for travelers and minimizing potential malfunctions within the arc. However, to begin, we should first establish and demonstrate a stable human civilization here on Earth.